So how are you guys? Can you see my screen? Okay. Are you guys at home or in the campus? Where are you? At home? Are you at home? Yes? Okay, that's good. All right, cool. That's good. So we're going to do the workshop, huh? We have 3 hours today and 3 hours on Tuesday and 6 hours on Sunday. Yeah. So I saw we have 36 of you guys here already. And I'm recording this lecture as well. Yeah. And so let's start. Okay. So for the lecture, so this is a pre-examination workshop. Okay, pre-examination workshop. Okay, so this is number 1, right? So I just give an overview. What are we going to talk about it? So we're going to do in 4 parts, right? So first part, we're going to do PID controller design. Part B, I'm going to do resident control design and analysis. Okay, and then part C. So I'm going to do an PID controller and implementation. And the final bit, I'm going to do cascaded PID control systems. Okay, so those are the 4 bits, yeah, we're going to cover for the 12 hours. And I will also show you guys, because the assessment will be when we have this exam, you're going to solve the problems, and we will also ask you to do MATLAB simulations, right? And so during this workshop, we also cover some of the MATLAB simulations as well. How do we, build those simulation diagrams? How do we get these things going? Yeah. But tonight we just do the examples. Okay. So if you guys can help yourself, can you please and use get yourself some pencil, paper, so we work together. So I'm going to do examples. Yeah. So I'm going to do lots of examples, and then we're going to start with very simple ones, and then we'll gradually go in for a more complicated one. I get paper and pencils, so sometimes I want you guys to do some work as well, because Otherwise, just like work. That's so I want you guys to do some work as well. Yeah. So we'll do some work together. So so I'm going to cover the first topic, PI controller design. Yeah. PI controller design. Okay. So what is a PI controller? So PI controller, we have time domain. Okay. So basically, we're going to in time domain, so we calculate the control signal u of t, right, equal to and kc, and reference signal r of t minus y of t. All right. So that's proportional control. That's a proportional bit, and then plus integral. So it's going to be kc over tau I 0 to t r of tau minus y of tau, right? And then d tau, right? So this is the PI controller in time, So we talk about the time domain. So we calculated the control signal u of t. All right. So in Laplace transform, right? Laplace transform. So what I have is u of s. So that's the control signal, right? Which is equal to n kc, and reference signal in Laplace transform, and then minus y of s, all right? kc tau I of s, right? R of s minus y of s. All right. So that's in Laplace transform, right? So in block diagram, what is this looks like? So you have a reference signal here, that is R of s, right? And so this is your feedback signal. So this is plus and then minus, right? Negative feedback. Okay. So this is you have this bit, right? So it's going to be kc, so 1 plus 1 over tau I of s. Tau I of s, right? Okay. So that's the output y of s, right? And then feedback here, like that. So this is your parameter transfer function g of s. So that's the Laplace transform. So it's basically this part is a proportional part, right? And this part is the integral part. So we can also put a different implementation, right? So we can put the proportional part in the output feedback only. So, but the integral bit has always to be on the main part, This guy has always on the tau I of s, right? So this is going to be a negative feedback, right? Kc, and the system g of s. Okay, so it's like that, So this part, what we have, if we do this, if we put a kc towards the output only, the negative feedback on this, negative feedback, then this structure we reduce the overshoot. So we reduce overshoot, right? So what is the overshoot? So basically it's like this. So if you ask the system to do a step change, say step change at 1, reference signal is a step signal, right? And then my output is going to go like this, overshoot the resistance. Yeah. So this is what we call overshoot. Okay. So if I use this implementation, I put a feedback KC on the output only, then my response is going to be like this. So you have 1, right? And instead of overshoot that, so they're going to go like this. Yeah, so like this. So this is what we say, reduce the overshoot. Okay, reduce overshoot. Okay, so this is PI controller, right? So you already have 2 different implementations, right? Even very simple, just have 2 parameters, right? But you have 2 different type of implementation, and then you're going to have a different performance. Yeah, well, what is that? Lost there. How does the second structure reduce overshoot? Because they zero. They don't have a 0. Yeah, that's a good question. And so, all right. So someone asked, how does the second structure reduce overshoot? So let's have a look. Yeah. So now let's give an example. Do an example. Yeah. Okay. So now say you have a first order. So for PI controller, right? We always we need a first order model. Okay. So first order model in this case, all right? I have a first order model. So G of S equal to 3 S plus 0.1, right? First order model. So I want to design a PI controller. I want the damping coefficient. Yeah, and say the bandwidth omega n equal to 1. Okay, so how I'm going to find the PI controller parameters, right? So that's a problem example, right? So we want to find KC and how I, yeah? Okay. Now solution. Okay, so your controller, so we have a C of S, right? Which is equal to KC 1 plus 1 over tau I of S, right? So I write it in terms of this structure. Yeah, so like that, right? So basically what is this? So I can, so basically with this, which is basically equal to, if I compare those two, yes, C1, and then 1 plus 1 over and C1 over C0 is, yeah, I can write it that. So if I compare this guy with this guy, yeah, then basically I'm going to get it and Kc equal to and C1, right? And then tau I equal to C1 over C0, right? So if I can find the C1, C0, then I can very easily convert these guys into Kc and then tau I. So my first step in the design, to find C1 and then C0, right? So the next step, Kc and then tau I. Okay, next step is to find the Kc and tau I, right? So now let's go C1, C0. Okay, so how I'm going to do that? All right. So what is the C1, C0? So when you look at the closed loop system, so this is what it look like. Right, first order. Yeah. Okay, like that. Yeah. So what is my closed loop transfer function? Like that, yeah. And 3 s plus 0.1, right, on top. Right. So this is equal to s plus 0.1 plus 3 C1 s plus C0, right? This is flip over. All right. So what is that? So I want to, this guy, yeah? So this guy is your closed loop polynomial. Yeah, closed loop polynomial. So the poles, right? The closed loop poles. Are the solutions of the polynomial equation. So this is 3 C1s plus C0, right? Got that right, yeah? So that guy equal to 0, that gives me the closed loop poles. Now, so what I'm going to do, so if I want to get the closed loop poles equal to the desired closed loop poles, right? So I basically make it this guy, right, equal to the desired closed loop poles. basically is equal to s squared plus all right, equal to that. So now I'm going to make it this guy equal to that. So basically, I got what is that? So C1, I compare, right? So basically, I'm going to compare coefficients of s squared, right? So basically, top is 1 and the bottom equal to 1. So I'm going to get 1 equal to 1. And then I compare s, right? So on the top, so it's going to be, what is it? Top is going to be 0.1, yeah, plus 3c1, then equal to 2 psi omega n, right? So I compare that bit. And last bit, yeah, is 3c0 equal to omega n squared. Okay, so now I compare this. So what I'm gonna get? So this gives me a solution, right? C1 is equal to 2 minus 0.1 divided by 3, right? So in this case, so I'm going to get 2 multiplies 0.707, and what is my omega n? Omega n equal to 1, right? And then minus 0.1 divided by 3, right? So how much is that? So that's going to be, so that's the answer, right? And then C0 basically equal to omega n squared divided by 3, right? So C0 basically equal to 1 over 3, right? So now once I get this, so I'm going to get a Kc equal to C1, right? And then tau I equal to yes. What is that? Can you type it? Can you type what is your question? Oh, no question? Okay. I saw someone's lower hand. Oh, no display? Ah. How can this happen? Now, can you see it? Can you see it now? Okay. Okay. That's good. Because okay. All right. So the tau I equal to so C1 over C0, right? So then you got all the parameters. You got that guy, and then you got that guy. All right. Okay. So now someone asked why the two implementations. Why the second implementation you don't have an overshoot, right? So let's see what is your first implementation. Okay. So with this implementation, right? Your transfer function is equal to this, yeah? Implementation 1. So Kc, so U of S, yeah? Okay, so you got that. All right, so use this guy. What is my transfer function? The transfer function y of s. So it's equal to, yeah, this bit, right? And then this bit, right? So it's equal to, right? Got this. All right. So this guy, yeah. So C1 equal to what? C1 equal to this. C1 equal to, yeah. So C1 is equal to 3, 2 multiply 0 0.707 minus 0 0.1, right? So this guy is the positive, right? And the C0 equal to 1 over 3 is a positive, right? So this is you have a 0. So this implementation, we have a 0. Okay, stable 0. So stable 0 is equal to C1s plus C0 equal to 0, right? So S basically equal to minus and C0, C1, right? So C0 over C1. So that's your 0, right? That's a 0. So this basically this is big. So this is stable 0. Okay, so the response of the stable 0 going like this. So the initial response like this. So the response on that is this guy. Okay, so that's caused the overshoot. Now if we put a KC on the output only, right? So what is your transfer function? So basically you're going to get something like this. KC over tau I S, right? Okay, like that. All right. So what is the transfer function from R over Y? So your transfer function, yeah, is going to be from this point, right? Your U of S is equal to Kc Y of S minus, right? And then plus Kc tau I R of S minus Y of S, right? So what is the Y of S? So Y of S is equal to 3 s plus 0.1 u of s, right? So I put this guy in. So u of s of s, and then you keep r of s, right? And then minus your kc tau I s and 3 kc s plus 0.1 u of s, right? So I move these guys over. So you move these guys over, right? So you're going to get it how much? So you're going to get it 1 plus 3 kc s plus 0.1, right? And then plus kc tau I s 3 kc s plus 0.1. Yeah, got that. Right. So now this basically you're going to get is so it's going to be your closed loop system, yeah. So basically your u of s over r of s. So I'm going to work this out, yeah, and then you're going to work out y of s over r of s. So in this case, you can go. It's going to be s squared. You can prove it plus 2 multiply 0.707 s plus 1, and then top is going to be 1. So this is your answer. If you put it, what is it? Put your controller, put your proportional control on the output only, yeah? Put proportional control on the output only, then you're going to get it's much easier. So your pole is going to be the same, right? But you don't have the 0. So you don't have the 0, so you don't have the big overshoot. So the overshoot is basically coming from this big 0 when you have the output versus your reference 0. Okay, so that's it. That's why you have an overshoot or not. Now let's do an exercise. Now it's not instability, it's a positive 0. Introduce the overshoot. Yeah, introduce overshoot. Positive 0, introduce overshoot. So negative 0 is if it's negative 0, so it's a negative 0. Yeah, so it's a stable 0, and introduce overshoot. It's unstable 0, produce a time delay. Okay. So if you have a 0, like the s minus something 0.1, right? Like that. Yeah. Yes. If you have a 0 like that, right? So it's unstable 0. Yeah. So this then is going to your response go like this. All right. The negative is unstable 0. So this is called the non-minimum phase. All right. So it's going to do like this. The response undershoot. So this causes this unstable 0 cause undershoot. Yeah, so stable zero cause overshoot. Yeah, yes, undershoot. Yes, correct. Correct, Benson. Yeah, so it's unstable. Yeah, that's called unstable zero. It's unstable zero because I make this guy, this is unstable because I make a minus s plus 0.1, right? Equal to 0. So s equal to 0.1, right? The positive 0. So that's unstable 0. But this is a stable 0. So this is a stable 0. Yeah. So this stable 0 is going to, so this means that if I s plus 0.1 equal to 0, then I got s equal to minus 0.1, right? So it's a stable 0, right? So this guy is called overshoot, this guy. Yeah, this causes overshoot. Okay. Okay. So now let's practice a little bit. I want you guys to do some work. Okay. So you guys got the paper? Yeah, got the paper. So let's do things, make sure we know what we're doing. Okay. So yeah, low zero, yes, and low overshoot, right? Yes, yes. Okay. Yeah, yes, correct. Yeah. All right. So low zero, low overshoot. Okay, so that's why you have low overshoot. That's why the two structures are different, because one already got you have a 0, and the other one doesn't have a 0. So now exercise, yeah. Okay, so let's design a PI controller. So what is it? So let's consider transfer function g of s equal to minus 10 s plus 1, right? Find the, I want you guys to find PI controller parameters. KC Pi, right? And I want you damping coefficient equal to 1 and omega n equal to 6. Okay. So I give you 5 minutes to work on this question. Yeah. See, you can do it very quickly. Yeah. 5 minutes. Yeah. Yeah. Okay. Very good one. So the implement now you're going to the controller parameters are the same. Okay. Kc tau I are the same. So you can do both. Okay. Both. See how it looks like. Yeah. The parameters are same. It's just that you do it. The only at the implementation stage is different. Yeah. Okay. Okay, well, what is Kc tau I? What is Kc tau I? Okay, Kc tau I. So C0 12, C1 equal to element over 3. So Kc then is equal to C1, right? And all right. So what do you have? Is so it's S plus 1, right? Someone, how someone got this number? So what are you gonna get? So it's A squared plus and 1 minus 10 1, right? So compare 1 minus 10 C1 equal to 12. Yeah, someone go, yeah. Okay. And then, so yeah. Is that right? I can count anymore. Okay. Right. So what is it? So C1 is equal to 12 minus 1, right? Divided by minus 10. So that gives you minus 11 over 10, right? And the C0 equal to minus 36 over 10, right? Who got it right? Let me see. Yeah. So someone got it wrong, huh? So C1 basically, so that's negative. So Kc is negative. Kc equal to minus 1.1, right? Tau I is positive, right? Tau I equal to C0 over C1, right? So equal to minus 36. Oh, okay. Minus. Yeah, like that, right? And so this cancels. So it's positive. Yeah. Say who else got this right? Yeah. Yeah. So Hawker got it right. Yeah. Okay. So this is negative. Right? But this is positive, right? Yeah. So this is wrong, right? This is wrong. This is wrong. All right. Good. I saw one got it right. Some people got it right. Some people got it wrong. Yeah, don't get it wrong. Let's get another example, another exercise. So you guys practice a few times and then you're going to be all right. Yeah. Now this is an unstable system. So I have an unstable system as a transfer function. Minus 2, yeah. So I want to put it, find the PI controller parameters. So I want to KC and tau I, right? And closure, all closure codes. At minus 2. Okay, so you guys can do this one. Huh? So I do 5 minutes to do some work. Yeah, do some work, 5 minutes. Anybody got a result? What about this one? Yeah. Anybody? Let's see if Benson said it's KC equal to 1, tau I equal to 3 over 2. Yeah. Yeah, S plus 2 squared. Very good one, Benson. Yes. So, yeah, very good. So let's see if Benson got it correct. So this one basically. Dealing with that with your mind. Okay. Let's see someone else. Okay, let's see. Okay. Okay. All right. C1, C0. Oh, okay. Very good. You didn't, yeah, okay. Very good. So what is it? So I'm going to get basically I'm going to solve for s minus 2, right? Multiply s, right? That's the denominator. And then 6 C1 s plus C0, right? And equal to s plus 2 and then squared, right? So my left hand side is going to be s squared minus 2 of s plus 6 C1s plus C6 C0, right? Equal to s squared plus 4s plus 4, right? Very good. So now I'm going to compare. So this guy and this guy, now good. So I'm looking at this and then this, right? So what I have is, so I compare s power 1 equal minus 2 plus 6c1, yeah, and then equal to 4, right? And then, right, 6c0 equal to 4, right? So this guy I solve. So what is it? So c1 then it's equal to 6, 4 plus 2, so it's going to be 6, yeah. So this guy is equal to 1, yeah. And then C0 equal to 4 over 6, right? So who got it right? Let's see. Yeah. So, yeah, KC. KC equal to what? KC equal to 1, right? Tau I equal to, what is it? And C1 over C0, right? Okay, so it's going to be 4 over 6. Yeah. And okay, got a KC wrong. Okay, did you get it? Should be 6 over 4. And yeah, good. All right, sure. Yeah, because this is on the bottom, right? Very good. So KC is equal to 1, right? Very good. Yeah, very good. Okay, so I pause a couple minutes. Can see everybody got it? So the key here is 2 poles at minus 2. Basically, we're solving this polynomial. Yeah, we use this polynomial equation. Okay, so very good, yeah. And now for design PA controller, right, we have to use what is a first order model. All right. So if the system is higher than, if the system is has a higher order model, second order system, second order model. Yeah, second order model. Yeah. Then we will do order model reduction. All right, we do model order reduction. Right. So let's give an example. How do I do model order reduction? Okay. So give an example, right? So if you have a system, you have one is that s plus 2, right? And another one is plus 10, right? Now, so this system, then I want to reduce this. A first order model. Yeah. So how I'm going to do that? So the trick is, so I'm going to make it this. So I'm going to write it in time constant form. So what I mean by time constant? So this one, g of s, right, equal to 0.1 So what I'm going to do, I take it, make it 2 out, and then plus 10 out, right? Then I'm going to go, so it's going to be 1 over 2 s plus 1, and then 1 over 10 s plus 1, right? And 0.1. Okay, so I take this post out and write it into this form. So this is what we call the time constant form. All right. So this is equal to what? Equal to 0.1 divided by 20, right? And so here is 0.5 s plus 1, and then here is 0.1 s plus 1, right? So this is smaller. This is smaller, right? This is smaller. So this guy is smaller. So what I'm going to do is I'm going to approximate one over like that. So this guy is approximately equal to 1, right? Approximately that equal to 1. Okay, so if I approximate that equal to 1, so this guy then is going to be approximated equal to 0.1 divided by 20, and then 0.5 s plus 1, like that. Okay, like that. Okay, so now I got my first order model up. Yeah. first order model. So then I can design PA controller for that. So what is it? So I'm going to design the PA controller. So basically, you use the model is 0.5 s plus 1 and 0.1 divided by 20, right? So I needed to write it. So it's going to s plus 2, right? And so where are we? Top. Then it's going to be 0.01. Okay, like that. So the PA controller, then we can find it, right? So we do exactly the same thing. So you're going to have s plus 2, right? Plus 0.01 C1s plus C0, right? Now I can put it over the closed pose. Say if we put closed pose at s plus 4, right? And squared, right? Then we can find C1. So C1 and then C0, right? Okay. Can you guys work it out for me? What is C1, C0? C1, C0. See if you guys got it right. Can, yeah. Who got it? What is it? So, yep. And no, we always change the pole further away from 0. No, I did this. No, I said it. That's why I changed it. I make this guy. This is I moved it. These two poles. Yeah, one is at -2, and then one is -10. Right? I removed this guy. Yeah, because I made the time constant to make it to write a different format. Yes, yes, yeah, yeah, right. Well, what is the number? Okay. Well, what is the number, guys? What is the C1, C0? Yeah. Ooh, okay. 1600. Okay. Okay. So what is that? So I compare it. Yeah. And 2 plus 0.01 C1, right, equal to 8. And the s of power of 0 equal to 0.01 C0 equal to 16, right? So C0 equal to 16 divided by 0 0.01, right? And C1 is equal to 6 over 0 0.01, right? That's good. So what I say, Kc is very big. Kc equal to 600, right? And then tau I is equal to C1 divided by C0, right? So it's going to be 6 divided 16. Right. Yeah. 6 divided by 16. Okay. So that's good. All right, good. So let's do one more exercise, and let's try one more exercise. Yeah, on this model water reduction case. So the system you're trying to go, the transfer function you have to do, G of S is a higher order. So you have for something like S plus 1, yeah, and then S plus 10. So we want to design PI controller. So the PI controller, we want to this guy, omega n. Okay. I pause for a couple minutes. Yeah, so let you guys do some work. Yes, Ben. It's good. Yes. 0.01 is plus 1. Yes, very good. So we have two poles at minus 10, right? And then it becomes, so you take it out, right? Then becomes, the gain becomes minus, it becomes 0.01. Yes. Yeah, very good. Anybody else see it? Okay, very good. So let's see if it's correct. So this is approximated, yeah? Yeah, like that. Okay. Yeah. So then I have yes, this plus 1, yeah, plus 0.01. Right. So I'm going to get and compare S. So it's 1 plus, yeah, 300. Okay. How can you get this 300? So this guy C1 is equal to, what is that? So this guy is negative, right? Is that? How can Ben, how did you get a 300? I didn't get a 300. Who got a 300? No, C1 equal to 100. First equation should be 4. Oh, yeah, yeah. Okay, good. You catch me, huh? Yeah, very good. Yeah, it's 300 and 400, right? Hmm? So now it's good. Okay, so your KC, right? Got it? Yeah. C1, yeah. 2 zeta omega n minus A, right? So yeah, correct. 2 zeta, zeta equal to 1, right? Omega n equal to 2, right? So it's 4 here. It's a 4 here, right? So 4 minus 1 equal to 3. 3 divided by B, 0 0.01 gives you 300. Yeah, correct. Anybody have questions? Yeah, very good. Okay, so now we're going to do, so that's a PI, right? So now let's do PID controllers. PID controllers. Okay, so this is the ideal PID controller, right? Ideal PID controller. So we still have the proportional bit and the integral bit and the derivative bit, like that, right? So you have extra bit is tau d, right? So this is what we're going to use for implementation. Yeah. For implementation before the filter, right? Okay, so because the derivative bit amplifies the noise, so we need to add a filter, right? So we have a filter. So the filter, what we're going to do is add the filter. We usually make it equal to 0.1 tau d of s plus 1, right? So because we're trying to, the filter is trying to reduce the effect of noise. Reduce the effect of noise, right? So I'm going to get it. So C of S Okay, so this is what we use for implementation. Right. So what we have, we can put it in the derivative term, always put it on the output only, right? So you're going to put it, you can put it a PI bits on the this guy, yeah. Right, and the D bits has to go to the output only. So this is your filter, right? Otherwise, you're going to amplify the noise. So the system, what you have, it's like that. Like that, yeah. Okay, so this is we use this derivative always on the output only because I don't want to reference signal change, make a big derivative kick on the system, right? So the derivative goes to output only. Okay, so when we design it, when we design the system, okay, we can yeah, we can use use this form. Right, like this. So this basically I can write it into what? I can write it as something like this. Right. So if I write this, I can see, so I go, this guy is going to be C2S. Right. I can do exactly like I had done before. Then, so this is basically I can get it as a C1, right? Take it out, and then 1 plus. So this guy then become 1 over C1, C0 of S, then plus C2, C1, and S, right? So if I write like this, then I can get it as a KC. Yeah, so you can do that. But it's easier to do the design use this form. Yeah, it's easier to design use this format. Okay, it's easier to do that. So let's do an example. Let's do an example. Yeah. So how about we take a break, then I come back and we do an example. Take a 10 minutes break. Then we'll do a PID example. 10 minutes break. Yeah.